So, for instance, what was I going to say? Oh, yeah. Sometimes when we get started, I put a little letter E there, okay? That little E is saying those are equilibrium concentrations. Equilibrium concentrations. Specifically molar concentrations. To just kind of hit you over the head, okay? Now, one thing we're going to talk about some kind of neat little things. You guys know that you can take a reaction and you can balance it. You can divide all the stoichiometric coefficients through by a constant and you get another balanced equation, right? We do the same thing with chemical equilibria. And there are consequences for the equilibrium constant. Okay? So, whenever you have an equilibrium constant, that's your capital K, lowercase c, if it's in molar concentrations, which is more common than partial pressures. Your KCs are written for a specific, not only just a specific equilibrium, but a specific equilibrium with a specific set of stoichiometric coefficients. So I'm going to talk you through what if you have the same balanced equilibrium and you have a different set of stoichiometric coefficients. You will have, put another way, a different KC. Okay? So, I'm going to kind of give you some examples. You guys did some homework where you came up with write the KC expression. You guys already have, is it already there? Okay, it's already there. So you already see the KC expression looks like this. Why isn't sulfur in your KC expression?
Because it's a solid.
Because it's a solid, exactly. It's always products over reactants. And I pause and think about that, and that's what it is. Well, what if we go ahead and what's the difference between, I'll call the first one equation 1, the second equation 2. What did we do here?
Multiplied by 2 to get rid of the
Yes,
fraction.
multiplied through by a factor of 2. And there actually, this is the equilibrium constant expression down here. So this is times 2, right? If you were to compare these two, actually what you did was to raise the quantity. Oh, how do I say this? I didn't do that right. Oh, go back. If you were to compare this one with this one, what you did was you took the quantity and you squared it. Right? SO3 squared, molar concentration of O2 to the 3/2. If you square that, what does that do? Makes it a cube, right? So it's a mini proof, but basically what I showed you is this relationship. If you have two equilibria, okay, with different stoichiometric coefficients, and as in the example here, if I double the stoichiometric coefficients, then I have to square the Kc, okay? So that's what that looks like. And if I would triple, I would cube the Kc, okay? Square root of, or sorry, 1/2, I would take the square root of. Let's do another little kind of thought process of what happens to your equilibrium constant expressions. So one of the cool things about equilibrium is they go from left to right, and they also go from right back to left again. So we're going to swing it around the equilibrium arrow and see what that looks like. Well, if this actually is our first expression, swing it around the reaction arrow, and this is our second expression. So what's the relationship between this one and this one? First letter I.
It's just the inverse.
Inverse. They're just the inverse of each other. Exactly. In this case, we kept the same set of stoichiometric coefficients. We just swung it around. What was reactants are now products, and what were products are now reactants. And then that made the equilibrium constant expression the inverse. All right. So this statement kind of shows you how that works. If you swing it around the reaction arrow, and let's just say you know the original Kc, that would be your Kc2, then your new Kc after you swung it around would be 1 divided by Kc2. Okay, so that's all that means. So those are tricks, actually, we're going to move into something, do you guys remember Hess's law, where you can add equations and get overall reaction of interest? Okay, so those are going to be kind of behind the scenes tricks. One more trick, and actually has to do with Hess's law. What if we have a Kc expression for reaction 1, or equilibrium 1? We have a Kc expression for equilibrium 2. We are going to actually add those two together, and we're going to get a third equation, okay, and it's the sum of the other two. So I was thinking in my, you guys have this on the next slide, I think, but let's just for kicks, underneath it, let's go ahead and write your Kc1, equation 1, okay? Again, solids don't appear, so it's pretty simple, right? It's always products over reactants. Their molar concentrations raised to stoichiometric coefficients. So I got CO over the molar concentration of CO2. You buy that, raised to the first power. For the second, okay, your equilibrium constant expression looks like this. Okay, this gets a little more complicated. All four of those things are gases. All four of them will appear raised to the stoichiometric coefficients, which just happen to be 1. So the molar concentration of H2 times the molar concentration of CO2 divided by the molar concentration of H2O. It's a gas, and it's not an aqueous solution. That better show up there. CO2 gas. Right? Now this thing down here at the bottom, this is actually 1 plus 2. Okay, how do I know that? Well, we've added equations before. I can kind of say, oh, those would cancel out. Oh, those would cancel out, right? And here's what I'm left with. So yeah, it is the sum of 1 and 2. So let's go down here and come up with our Kc3. Okay, solids don't appear, so my iron 2 oxide is not there. So it's looking like this. H2, molar concentration of H2 in the top. In the bottom, iron doesn't appear, molar concentration of H2O. Okay. I'm going to prove to you, actually the proof is right here. Do you see where if I take this quantity times this quantity, I get the third quantity? My CO, oops, sorry, I did something wrong here. This should be CO, sorry. My COs cancel, my bad. My COs cancel, my CO2s cancel. I'm left with H2 over H2O2. Okay, so what I just kind of showed you was this. If you can add two equilibrium together, and you have equilibrium constant expressions for both of them, and in this case we're getting a third chemical equilibrium, the Kc expression for the third chemical equilibrium is the product of the other two. That's all this is saying. Kc1 times Kc2 is equal to the third one. Okay, so that's how that's the last trick. All right. So let's kind of do an example to kind of get our feet wet with using equilibrium constant expressions, and also to kind of use the tricks we just talked about. So what do these little E's stand for? Equilibrium, yeah. So it's kind of cool. On the next slide it tells you what it is, but can you see where we can actually lift from the paragraph, from the words there, and write this? It says, can't remember which way I'm writing it. Well, we've seen this before. This is sometimes called the Haber process, where you have nitrogen gas plus hydrogen gas going to form ammonia. Now this totally is not balanced. Oh my goodness, put on our Chem 1 hats. So if I want to leave that a stoichiometric coefficient of 1, and from the N2, this will give me 2 here, and I put a 3 here. Does that all work for everybody? Okay, those are my stoichiometric coefficients. Okay, so there would be a Kc expression for that. So, and I can't go back and forth, but you guys can in your notes. These are the equilibrium concentrations. Put another way, and I'll just kind of pick on this one. Okay, this might be our first equilibrium. I'm not sure. You know, we could go ahead and write the equilibrium constant expression. So it'd be what? NH3 raised to the second power divided by molar concentration of N2 raised to the first power times the molar concentration of H2 raised to the what power? Third, yeah. All this says, and it's pretty exciting, I don't mean to overstate this, but I can take those 3 molar concentrations, which I will here in a minute, and I can plug those in here, square the NH3, 0.016. In the denominator, we have the product of the 0.030 times 0.037 raised to the third power. You divide that out and bada boom, you have a Kc, okay, for this equilibrium with those equilibrium concentrations. So actually we're going to pick on that one first, and then we're going to switch gears. What is the difference between 1 and 2? So this is going to be our Kc2. Just switched around reverse. So what's the relationship between our Kc2 and our Kc1? The inverse. Yeah, exactly. But we're going to kind of mathematically work through that proof. We're going to take those same 3 equilibrium concentrations and prove to ourselves that the Kc2 is actually the inverse of Kc1. And then what about this one? What's the difference? Let's pick on second and third. What's the relationship between second and third? This one's multiplied by 2. Put another way, this one is multiplied by 1/2, exactly. Okay? So actually, we could take whatever this Kc2 is and raise it to the 1/2 power and get your Kc3. We're going to kind of prove ourselves with those equilibrium concentrations. All right, so it looks like this. Picking on the first one, those were the molar concentrations of your stuff at equilibrium. So we just kind of plug. I guess I shouldn't make this harder than it is, right? We can come up with your equilibrium constant expression, okay, for those 3 species in chemical equilibrium at that temperature. Okay, your Kc value. Now, do you remember what are the units of your equilibrium constants?
There's no units.
They're unitless, right? So notice I'm kind of taking the cheap way out. I'm even putting the letter M after that for molarity. But when you do that round to 2 significant figures, you get 1.7 times 10 to the second. So that's 170. Yeah. We talked the other day, do you buy this? That to me, it kind of favors the product a little bit. Okay, because it's kind of moderately, it's not way above there, but it's a little higher on the past one. So that's our answer here. Let's go on to the next one and see what we got. Now, you said the next one, I just kind of switched it around the reaction arrow. I could write the Kc, or equilibrium, you know what I mean, equilibrium constant expression, and it looks like this. Basically the flip of this. Where now our products are the N2H3, now our products are the N2 and H2. So we have molar concentration N2 raised to the first power times molar concentration H2 raised to the third power. And our reactant is ammonium, with a stoichiometric coefficient of 2. So that goes in the denominator. Now you know what I'm going to do? I'm going to take those 3 numbers, bless you, and I'm going to plug them up. I'm going to plug them in. Okay? So that should seem kind of familiar. 0.030 times 0.037 cubed divided by 0.016 squared. The value your calculator gives you would be 2 sig figs, round of 2 sig figs, be 0.0059. Which, if you take that value and you take 1 over x, okay, you will get 170, which was your Kc1. Isn't that wonderful? So it's kind of like a little mini proof. All right, last one. You guys told me the last one was, this is the third one. So Kc3 actually is related to Kc2 by quantity to the 1/2 power. Let's see. Now, if I was going to write the equilibrium constant expression, it would look like this. So it's always products over reactants. In all cases, rate their molar concentration raised to stoichiometric coefficient. So we have molar concentration at N2 raised to the 1/2 power. Now this is one where my fingers feel fat on my calculator. I'm like, oh, I have to do it a couple times to convince myself. Molar concentration of H2 raised to the 3/2 power divided by the molar concentration of NH3 raised to the 1st power. So substituting in our equilibrium concentrations, it looks like this. We have 0.030 raised to the 1/2 times 0.037 raised to the 3/2 divided by 0.016. And I don't have an easy way to kind of show you working these. I told you I feel like I have fat fingers. It's definitely doable, okay? But when you do that, you end up with a value, 2 sig figs, of 0.077. And we could do a check on it. If you were to take KC2, which are the 0.0059, and raise it to the 1/2 power, ta-da, you get 0.077. So I like this example because it also kind of talks you through that if you have different balanced equilibria, by golly, you're going to have different KCs. You just are. So your KCs are for a specific balanced equilibrium. But you should be able to kind of go back and forth between the equilibrium. So these will be due on Wednesday. Be here before we know it. I hate to get you guys too excited, but let's see. The first Monday in April, I won't be here, and there'll be other instructors that will be gone that day. But I think I might have them come and administer a survey. So I wasn't going to tell you I wasn't going to be here. But I'm going to be here next Monday, but not the following Monday.
I actually already did that survey.
You did that survey? Oh.
I did too.
Did you? You might still.
I was going to, but I had to do your homework instead. So.
I got an email about a survey. Is that the survey you're talking about?
No, that's a different
Oh, that's a
survey.
different
I'm
survey?
excited about that
Okay.
survey. Oh, you already did that one?
Yeah.
Yay! No, that's the one. That's the cupcake survey. So we need at least one of you guys others to do the email one, and then we'll have cupcakes. Okay, on the Friday after it closes. But no, this is a different one. This is a general. This isn't related to a teacher. It's just related because that's why you said that.
Oh, okay.
It's related to your experience here at the college, not related to a specific teacher. It's confusing. Like, don't you feel like
Another email about that one.
surveyed out sometimes? That
Well,
could be.
like specific classes will be selected to complete the survey.
Yeah,
Is that what
yeah,
you're talking about?
yeah. So there's two. There's one for the instructor, and you have to do that for cupcakes. And then there's one other general one. So I'll think about it. I don't
So
know.
I have to ask for money for these surveys. Too much of my time.
Yeah. Time is money. So, if it's okay with you, I didn't look at these, so this could be dangerous. I do want to do the next part. So let's go take a quick look, though. These I had posted before, a year ago. Ooh, where are they? Okay. But before you came in, Mike, I warned y'all that Units 3, which you're in now, in this class, and Unit 4 are very closely related.
Excellent.
Good. So keep up with the homework and keep up with what's covered, and you'll be glad for it. Okay. Okay. All right. Let's see what we got. So you notice that I have the red 1 and 2 over there. Those are kind of, in Hess's law, those are like your baby equations, okay? And the equation of interest is up there with a star. So it's kind of like, some of you liked Hess's law, some of you didn't, okay? But basically you're going to take these two and kind of manipulate them to get your equation of interest, okay? So, yeah. Remember, when reversing, it's the inverse, okay? And when you multiply, it's raise it to the power, okay? And then last but not least, I don't think I have it on here, but remember when you add KC1 plus KC2 to get your reaction of interest, then you multiply them. It's a lot to remember, but your problem, not mine. Okay. This one, you have 3 baby equations to get the overall reaction of interest. And I even have hints here. Sometimes my hints, I don't know if this is the one that is, but they aren't always right. So I hope these were right. I sure didn't mean to set you up. I'll just kind of show this whole thing here. Okay, my hint in orange down here is that, or green and orange, I call them intermediates. I don't know if I'd really call them intermediates, but there's something that needs to cancel out and not appear in this reaction of interest. Okay, and you guys did this in Hess's law. You have to kind of monkey with the stoichiometric coefficients to make them cancel out. So it's all fun and games till someone gets hurt. Reaction of interest, got a star up there. You have 3 to work with. Notice, let's see, in green here I say, use process described previously to get your KC. And we talked about the relationship between KC and KP, and that was what some of the homework that was due today was. So you're going to have to do one last step there. Okay, we should be fine. I don't see anything. Again, okay, let's see what this one is. All right, this one looks a little more interesting. So we have equilibrium amounts. This is a good example of, what do these brackets mean? Molarity. Can you guys go from grams to moles? Mm-hmm. So you're going to have to do that. They're all in their gaseous state, so they fill that container. So put on your Chem 1 hats and take those grams, and yeah, that was my hint there, I guess. And there's your equilibrium constant expression. Oh, but anyway, I think you're fine there. Okay, so in an ideal world, I may not do these back to back, but we live far from an ideal world. Okay, so this is so cool. I just love this material. And if you're kind of think numbers are kind of fun, I hope you do too. So this is called an equilibrium constant expression. Before I show you a slide, I'm going to put something up over there. Check this out. I'm going to put Q, I'll go ahead and put C1 because it's 1, is equal to molar concentration of NH3 squared divided by molar concentration of N2, the first power, molar concentration of H2 raised to the third power. Let's see, what else was I going to do? Oh, yeah. I'm going to put E's here. What do E's mean?
Equilibrium.
At equilibrium. This is your equilibrium constant. I'll just put eq constant. Okay. This is your reaction quotient, RxN quotient. My thing is, do you see how similar they are? All right, but what's different between the two?
Not at equilibrium.
The not at equilibrium, no little e. No little e, exactly. This is like I call this a snapshot of your chemical equilibrium. Okay, it could be any time. It takes a while for the dust to settle. It takes a while for it to be the same rate in the forward direction as it is in the reverse direction, to have a constant amounts. Yep, that's it. Totally. So QCs, they take on the same form as KCs. Okay, this is your reaction quotient. Sometimes I have a hard time thinking of the name reaction quotient. But like I said, it's a snapshot, and this is not necessarily, oh goodness, you know what I mean, not necessarily at equilibrium. But this is at equilibrium. Okay? That's it. That's it. So as you might imagine, we kind of have some relationships, though, between your reaction quotients, not necessarily at equilibrium, could be, and your equilibrium constants. We're going to I'm going to talk you through a very important type of problem is basically, I'll put A here. A is in what you do. A, you take a snapshot, and then B, you compare your snapshot, which is your equilibrium, which is your reaction quotient, compare QC to what the textbook tells you your equilibrium constants are. And then you can make some judgment calls there. First off, if they're equal, what does that mean? Like if your QC is equal to your KC. It is at equilibrium, yep. Exactly. So here's your possibilities. The first one is just what you told me. If you take a snapshot and your reaction quotient, QC, is equal to K or KC, bada boom. You are at that sweet point. The rate in the forward direction is equal to the rate in the reverse direction, which means you have a constant reactance products. Now, we have a couple other possibilities. If your reaction quotient is, I could say, too small, if your QC is too small compared to your KC, what I think of then is I look at my QC and I'm like, oh, this is, let's see, it's too small. This is too small. And what is this? This is my product. Okay? So what that means is it has a little bit more to go that way to reach equilibrium. Okay? So if your reaction quotient is smaller than your equilibrium constant, then it needs to, what we say, proceed from reactants to form products to reach equilibrium. It's not done yet. Not done cooking. And the direction it has to go is what we say to the, I get my left and rights mixed up, what we say is it has to go to the right, as it's written. Yep. Cool. So we have equal, less than, and the last inequality would be greater than. So if your QC, your reaction quotient, what I say is too big means we have too much products. So that's actually going to mean it's going to have to unconvert some of those products back into their reactants. Okay. So in that case, it needs to go ahead and we say proceed backwards, kind of, from products back to reactants. Which it's an equilibrium, it really doesn't care what direction it's pointed, kind of. Okay. And I guess we would call that, we kind of left and right, we would say it has to proceed back to the left again. Right. Okay. So let's look at an example. Let's kind of read it carefully, make sure we kind of know what's going on here. We have, we're given in molar concentrations of all three of these gases. They all happen to be at 0.0020 moles per liter. Okay, so that's all to say the equilibrium concentrations are, sometimes I would write it like this if I'm feeling kind of, I put a little, no, I don't put an E there. Molar concentrations, because we're going to actually take a snapshot. And molar concentrations are equal. If you read it, actually, I think it says question mark at equilibrium, and if it's not, which it's not, at equilibrium, which way will it proceed? Is the system at equilibrium? Which won't be. So if it's not at equilibrium, which direction does it need to go in order to reach equilibrium? Is your KC large? In which case it needs to go back and form reactants? Okay, is it small? So it needs to go forward and form reactants. Excuse me, go forward and form products. Thank you, yes. Okay, so the first thing to do is to come up with your KC expression. Excuse me, your QC expression, which just looks exactly like your KC expression. Okay, snapshot though. These missing the little E. So if we go ahead and put, and the math is pretty easy here, right? Like, oh, that is so fun. okay? Because the molar concentration for everything was 0.0020. So notice that everything cancels, okay, and gives you a value of 1. Isn't that fun? Yeah. So that's what our snapshot says. Now, I missed it. On the previous slide, did it tell us what our KC was? What was it?
46.
46? Ah. So we're coming in on the low side. Yep. So the fact that 1 is less than 46 means we need to go which direction? It's too small.
4 more products.
To 4 more products, exactly. So that's the last question here. Yep. So the fact that 1 does not equal to 46 means it's not at equilibrium. And the fact that 1 is less than 46 means we need to beef up our products. Now, if you're faced with a question like this on the test, you can't guess. You have to go through this process. A 50-50 chance, I know. Or like a third chance if you kind of figure it could be an equilibrium, right? But
33% chance.
right. You have to go through this, which isn't too bad, really. Any questions about that? Okay. Dang, I must talk really fast. So let's take a quick look at these, and then that will be enough for today. 1529. Where'd you go? There you are. Oops. Okay. So, again, you're not given molar concentrations, drat, but at least you were given moles instead of grams. You can do this. Divide the moles by the volume to get the molarity. So I usually, you can't go wrong in writing your equilibrium constant expression. Of course, I have Kc here, and we're actually going to come up with Qc first, aren't we, to compare it to our Kc. So the QC expression looks like the same. Okay. Notice I put little zeros there. What do you think that means? Initial. Yeah, that means initial. You're going to kind of let the dust settle. And actually, we're going to do a related problem where you're going to kind of take the initial and apply a change and come up with equilibrium concentration. So that 0 really is kind of significant, I think. Okay, so I think you're fine there. So plug those molar concentrations into your plug those concentrations into your reaction quotient expression, okay, and then compare it to 100. If they're not equal, then it's not at equilibrium, and you have to say what direction it's going to go. Or I think there you don't have to say what direction it's going to go, but I think you should. All right. So much previous. Okay, that's good. All right. The next one, or the last one. Oh, tricky. Tricky part here is setting up molar concentrations. Let's see, what are you given? Oh, all right. I don't like this one. You make this one extra credit. This one's irritating. Extra credit, 32, but let me know if you do it so I can make sure I give you the extra credit. And I'll go ahead and show you my hints. It says equal masses, but of course, they have different molar masses, so they have different moles. Okay? So what I did before is just, see, what did I do? Well, I don't know. I haven't looked at it recently. So I'm going to push my hints out there. Okay. But you should be able to have your masses basically cancel out, just only in this case because you have equal moles on both sides. Your masses will cancel out, and you'll be left with working with your molar masses instead. Okay, it wouldn't always work this way, but it does this time. Okay, so.
So it'll be, end up being instead of the molar mass per volume rather than.
Right.
Okay.
Yeah, I think so, if I remember it right. Yeah, I just think it's irritating, but yes. And it wouldn't be this sweet if it, yeah, if they didn't all cancel, then you'd end up with a variable you didn't know what to do with, but they will cancel. Okay? Yay. That's it for today. We'll see you tomorrow. Wait, you know what I mean.